Well, hello and welcome to the next day DevNation Live. I'm actually coming to you live today from Dublin, Ireland, where I was just in Westford, Ireland with Clement, but I had to leave him to catch my next flight. So he's still out in Waterford, Ireland, and you can see with his nice green background there. You got the whole Irish thing going properly, thank Clement. But we have a great session lined up for you guys today. We're going to be deep diving into the reactive landscape. If you're familiar with reactive programming, that's awesome. We're certainly going to tell you give you some insights onto reactive programming, but also the reactive systems architecture that you might be thinking about for the next generation of your applications. Clement is absolutely our expert who goes out and talks about these topics on a regular basis. He's from the Vert.x team specifically, but his background is fundamentally focused on how to build reactive systems, and I think you're going to really enjoy today's session. So Clement, please take it away and let's see what you got.
Okay, thank you, Bear. So let me share my screen. Okay, and switch to present mode. All right, so my name is Clement Escoffier. I'm working the Vert.x team at Red Hat, and today in this session, I'm going to explain what does reactive mean, because today you have a lot of reactive things, and if you Google about reactive, you will find things about Manifesto, Reactive System, Reactive Streams, Reactive Extension, Reactive Programming, Reactive Springs, and if you dig a little bit deeper, you will find that reactive is often associated with many different concepts, such as back pressure or events or elasticity and even spreadsheets. But seriously, what does reactive mean? So let's have a look to the dictionary. And if you go to this page here, to the Oxford Dictionary, and search for reactive, you will find this. Reactive means that you are showing a response to a stimulus. And there is a second definition here, which says that you are acting in response to a situation rather than creating and controlling it. So if we take those two definitions and we want to say what is a reactive software, we can come up with this. A reactive software is a software reacting to stimuli such as messages, requests, metrics, availability, or anything. Cool. But let's have a look to this definition here, acting in response to a situation rather than creating or controlling it. That's actually very interesting because it's at the end of the flow control. Right now, when you're creating an application or developing an application, you have you do something A's and B's and C and so on. So you know exactly when things happen. But when you are doing something reactive, things are a bit more tricky because what decide what's next is the next stimulus that you are going to receive. So basically, this is the revenge of the asynchronous system or asynchronous API we had in the 80s and so on. So we are going to see how this actually is going to change how you build system. But just to have some better understanding of what I mean by reactive, and what is the reactive spectrum is that we have many reactive things, as you have seen. So let's try to categorize this. So on the left side, we have reactive systems. And reactive system has been defined by the Reactive Manifesto. We found concepts like actor, messages, resilience, elasticity, scalability, and asynchronous. On the right side of this slide, we have reactive programming. And while reactive systems are on the architectural level, or to build distributed system, reactive programming is really about the development model to build event-oriented or message-oriented and asynchronous program. And here the concepts are totally different. We are speaking about streams, flow, events, and of course, asynchronous. And there is a third reactive thing that is very important today. It's reactive streams. Reactive streams is a model of back pressure on non-blocking back pressure. And here we have different concepts associated to it, like data flow, back pressure, non-blocking, and asynchronous again. What is interesting is that today, and since a year or a year and a half, these two ones, reactive programming and reactive streams, start to be the very same thing, in the sense that the new generation of reactive programming library are leveraging reactive streams as a basis to handle back pressure. So don't worry, we are going to explain all of this. If we are looking in terms of technologies, in terms of reactive system today, in the Java world, we have Akka, a pure actor model, and Vert.x. For reactive streams, we have Akka Streams, Eric's Java version 2, Reactor from Pivotal, and Vert.x. And in terms of reactive programming, we have Reactor, Reactive Spring, Reactive Extension, with Java in the Java world, and Vert.x. We can find Vert.x on these three different reactive thingies, and we will see how Vert.x is a bundle for all of this and how you can leverage from the ability to use these different concepts. So, but let's go back when I was young and I was doing a very simple application. It's almost 20 years ago, and my application was very easy. I have users that was entering data about products and was looking for data about this product. So I got a very beautiful form where they were entering data, and then I was saving that in a database. Everything was fine. I was very happy. It was working, almost no crash, and so on. But one day, the code base started to be very, very complicating and was growing, and we asked me to extract some part of this data inside another services, the pricing service that would be handled by another team. Okay, why not? So every time that my application needed a price, it will call this service, get the price, and display it to the user. Okay. Obviously, there is a mirror of this, is that my application started to be used by some other services, some other software from my company or from other company. And okay, so I had to develop an API in addition to my beautiful form, so they can call me and I can give them the products and the price and so on. But then users were tired to refresh the page to get new data and so on, and they wanted to get notifications. It's something we have a lot more today. While you have a mobile phone and so on, you get notification all day long about your mails, about messages, and so on. So they don't want to refresh anymore. They want the data to go to them. So we needed to implement such kind of channel. And as my application started to be a lot more complicated than before, we decided to add some logging, monitoring, auditing, and so on. So add complexity and so on. But something we forgot when we did all this transformation is that all these interactions are distributed interaction. We are not speaking inside the same memory. So we are crossing the process space. We are discussing with the database over the network. My other pricing services were over the network too. My users are definitely over the network and so on. And there is one thing that we know about distributed system is that distributed system fail. They fail for many, many reasons. Well, there is data loss, there is latency, there is timeouts, there is slowness. For example, my service here may not be ready to answer my request because, well, it's either in a pretty bad shape or under reload or under maintenance or something like that. My database can become very slow, not necessarily because of my database, but because of my network. I don't control when my user or the other software are going to call my application. So I don't know, I cannot really predict the load. So it was very, very complicated to get all of this working, and the capacity planning was very complicated. And what happened was what we all know about distributed system is that my monitoring was telling me that I was dying. So the whole system was collapsing under the load and so on. So the main question is, how can we stay responsive in face of failures and under varying workload when we don't control anything? And actually, that's exactly the purpose of reactive systems. The goal of reactive system is to build a responsive system. So it's an architectural style to build better distributed system based on one primary concept, which is message-driven. All the interactions are going to be using an asynchronous message passing mechanism. And based on this, we get elasticity and resiliency. And if we have all three, then we get responsiveness. This has been defined in the Reactive Manifesto that you can find here. It's very nice to read. It's very short, so I recommend you to read it. It's really interesting. Okay, but how it works? So basically, we have all our entities that will interact using messages, and messages are not sent to a specific recipient, but they are sent to an address. And on the consumer side, you subscribe to the address, and you get the messages when the system decides that you are the next one. So if you have a lot of messages, you just need to scale or to increase the number of message you have here, of consumer you have here, and it will just dispatch using a round robin or something a bit smarter than this. if one of my consumers fail, well, the message can be processed by another consumer. And something that is very interesting is that the publisher won't wait in an active way for a response. Everything is asynchronous, so it can continue under other messages and send other messages using very few capabilities and memories and CPU. Everything will find perfectly well. So when you see this, you say, well, okay, come on. Everything is simple. We'll just do that all over the place, and I would just send messages and receive messages and get replies, everything asynchronously, and everything is fine. But if you try to implement this specific application on such kind of application without really thinking about it, very quickly, you get this. You get this very complicated code with callbacks and a lot of threads that are going to try to conflict. And what happens when threads try to conflict? Well, you get deadlocks or live locks. So it's even worse than what we have before. So we need a better way to handle this. So let's see how we can do that. But before doing that, let's explain why it's complicated by introducing you to the asynchronous development model. In the ideal world, when you have three things to do, you will do the first thing, then the second thing, and the third thing, and everything will be fine, and you're done here at that point in time. But in the real world, we have I/O, and this task A will be blocked because it's calling another services or doing, for example, my pressers or something like that, and for that time, it's waiting. So my thread is blocked. And when I get the reply, I can continue and so on and so on and so on until I'm done. And then I can do task B, which will do some other I/O and so on. So in reality, you're not completing your work here, but here, way longer. And during that time, all this waiting time, you just do nothing. You just wait. And we don't like waiting. So the asynchronous execution model is a bit different. You say, okay, we're not going to wait. But as soon as we have to wait, we will try to switch to another task that can make progress. And when we can't make progress anymore, then we will switch to another task. And maybe when we can't make progress anymore on that task, we can switch back to the first one because we finally get an answer. So instead of explicitly waiting, we will try to always stay busy. So because of this, we are back to exactly the same time. We even get some free time here to do something else. But to do this, we need three things. We need an asynchronous programming model, we need non-blocking I/O, and then we need a task-based concurrency instead of thread-based concurrency. And when you do that in your code, things start to be a bit weird. Generally, we do that. I have my compute method, I pass parameter, and at some point I return the result. And on the consumer side, I just get the result like that. But in an asynchronous world, it's not working like that. It's the Hollywood way. We pass the parameter and a callback. And when the method has computed the result, it will call you with the result. So on the consumer side, if I'm using Java 8 Lambda expression, I will use compute, I pass my parameter, and then this will be my callback here. And it will be called when my result is there. Everything fine. Why not? Let's have a look. So if I'm using Vert.x to create an HTTP server as an example, every time that I have an HTTP request, I will call this handler here. Okay, fine. And every time I have a new request, I'm going to call this again and again and again. And to start my HTTP server, I will use this method here. And this callback here will be called when the HTTP server has actually is started or failed to start, because obviously there is many reasons why it can fail. So looks nice. The code is okay, but let's have a look to another example. I want to retrieve data from a database. So I need a connection. This is going to be asynchronous because getting a connection is asynchronous. Then I need to do a SQL query, for example. This is also asynchronous. So I need to do another callback. And obviously, when I'm finishing processing the data, I need to close my connection. This is also asynchronous and a third callback. So we need to face it. This is not code that I want to write and read every day, because even if this is relatively easy, it doesn't scale. And all the Vert.x ecosystem is developed like this. And believe me, it's not easy every day. well, we do that because we don't want to depend on anything, and we want to have something homogeneous. But yeah, it's kind of, sometimes it's hard to read. So what can we do? How can we fix that? And it's where we have reactive programming. And reactive programming actually has been designed a long time ago. And the idea is, how do I write code to handle asynchronous events and streams? But to explain it, the best example is spreadsheets. So I do a lot of meeting, conferences, and so on. And the most painful experience is my expense reports. But fortunately, I can use Excel to at least prepare my expense report. And this is reactive programming. So I have, for example, lunch, coffee, drinks, and this is the total. But if you're an Excel user, you know that this is actually a formula that is expressed in terms of the other cells. Right? So there is an observation. So as soon as one of these cells change, these cells observe the change and recompute the new value. And over time, we have something very interesting happening, because at the beginning, I have only my lunch, 15 euros. Okay, so this becomes 15. And then I answered 25 coffee because of jet lag. I need a lot of coffee. So this is 40 euros, and then a lot of drinks, and then I'm at 85 euros. So over time, a cell is not one value, but a sequence of value. And it's a stream of value. So the stream of value, depending on the technology or the reactive programming technology you are going to use, have different names. It can be named observable, flowable, flow, or publishers, depending on what you are using. But if we are using, we are going to use Eric Java 2, and we are going to use the flowable concept. But to give another example, because that's what reactive programming is about streams. Let's have this red stream here with this sequence of integer. And then I want to have another stream that take all those data and just do +1. That's my green stream. So every time that I have a new data in my red stream, I have this a new value in my green stream. And let's do something a bit more complicated in my blue stream, which will subscribe to my green stream, get the two last value, and do the sum of it for any reason, whatever. If I want to express this using Java, for example, Eric Java 2, I will do like that. First, I have a stream named flowable of integer, which will be all the integer from 1 to 10. And then I have my green stream, which will be subscribe or observe the red stream, obs1, and map all the value to the value +1. Okay, why not? So this will be my green stream, and will be exactly this. So for 1, it will give 2, 2 gives 3, and so on. And then I have my blue stream, where I'm subscribing and observing the green stream, get the last two value, and every time that I have two value, just compute the sum of it. So it's actually interesting what's happening here, is that here we have flat map, because map associate to one value another value, while flat map associate one value to a sequence or a stream of value and just flatten this set of value. So yes, the sum of two integer is just an integer, but the API is like that. And don't forget this. This is probably the most disturbing thing when you start using reactive programming. If you don't subscribe, nothing is going to happen. It's very lazy. So you need to say, oh, by the way, all those transformations has a purpose, and the purpose is that I need the result. So don't forget to subscribe to your sequence of streams. So here I'm subscribing to the green one that will then enable the blue one, then enable the green one, and enable the red one, and everything will start working. Okay, so but what's the relation between this and the asynchronous thingy I was mentioning? It's actually because the stream is inherently an asynchronous structure. For example, a flowable or observable are a stream of data. So every time I have an HTTP request, I will be invoked and I can do transformation on it. There is another type of stream which can have only one value, like singles, or 0 or 1 value, like maybe, and this will be used as asynchronous operation. I need to call my parser service. I don't know when I will get the reply, but I know that we'll have either a response or an error, and this is what a single type is made for. we also have completables, which are for asynchronous operations that have no return. So let's say, okay, tell me if you have completed or not, like writing somewhere in a file and stuff like that. And it's interesting because you can use those reactive types of flowable, observable, single, maybe, and completables to really write and develop all your asynchronous system. But we will see an example of that in a minute. So typically, if I want to rewrite my JDBC or my database interaction, first I need to get a connection. So I will use this method here that gives me a single, so a stream of one with the connection. Once I have my connection, I say, okay, once I have my connection, execute this query here, select star from products, so get all the products, get all the stream of row and transform it to a flowable, so to a stream. And when I'm done iterating over the stream, just close the connection. Fine. So, and for every row I got, I will create a new product using some kind of ORM mapping or whatever, and I just subscribe to that. That's exactly the same code I was showing with my 3 nested callback. And now we have a way more declarative way to express exactly the same thing. And what happened is actually this. We have the singles, and I do my query. I get my query here. I get my sequence of row, and I map it to product, and then I subscribe here. Is that all working? Well, maybe something is not that simple, actually. And we are going to see that now. What happens if at some point here, something very slow is done, like instead of just displaying the product on my cursor, I'm actually doing very heavy computation on it. If I'm in a blocking environment, what is going on is that it's going to block my thread till the beginning. But maybe you can't do that, because maybe the thread that is producing the data is not the thread that you are using here. So what's going on in that case? What can happen when your processing can't keep up? Well, what happens in every case is we are going to fill a buffer. And what happens when the buffer is full? It's going to crash out of memory, or in Rx we have exception for that. But yeah, well, buffers are limited, so you need a way to handle this. If you can accept to lose data, well, if data loss is acceptable, just say it and say, okay, my buffer is only 3. And as soon as it's full, all the new data, I would just redirect them to /dev/null. I'll just ignore them. So obviously, you can tune it to have the last that is drop, or the first that is drop, and so on. But that only works when data loss is acceptable. But what about when you can't have data loss? So then we need a protocol between the consumer and the producer, so between the 2 streams, to say, well, I will tell you when I'm ready to receive, and don't give me any data until I'm ready. This is actually what is done by Reactive Streams, which is one way to handle back pressure in a non-blocking way. And how it works is that my consumer stream here is actually going to ask this stream to say, okay, I'm ready, give me X element. The element will be produced asynchronously when they will be ready. And when they are processed, this stream can say, okay, I'm back on track. Just give me another set of X elements, and so on. So it's interesting because all the stream semantic is about pushing data to the next one. And here we are reversing it to say, no, the consumer needs to say when you are ready, and so on. But it's mandatory if you don't want to crash and to collapse under load or under way too many data. Actually, for you, if you're using Rx Java 2 or Reactor, you don't need to care about it, because that's what Publisher or Flowable are implementing behind the scene. Flowable and Publisher, so actually Publisher is a Reactive Stream type and Flowable is an implementation, are just stream implementing this semantic, so you don't have to do it. It will just work out of the box. While if you're using observable, then you're on your own, and you will have to handle the back pressure as you can, using your own protocol. Okay, but Let's now have a look to Vert.x a little bit more and explain you why it's interesting for you if you are looking for reactive. And it will give you a better understanding on how all those concepts work all together. So reactive system, reactive streams, and reactive programming. So what is Vert.x? Eclipse Vert.x is a toolkit to build distributed and reactive systems. It's just a library with a large ecosystem, and all this ecosystem is reactive, and it has been designed to be reactive in mind. It's not something we have added as an afterthought. The first line of Vert.x was reactive, so we learned a lot by doing that. What are the issues, how to handle blocking code, non-blocking code, and so on. It's proposed not one, but several asynchronous non-development models. If you want, you can use callbacks, you can use Heroic Java 1, you can use Heroic Java 2, but it's also polyglot, and you can use Scala, Kotlin, Groovy, Ruby, and Ceylon. And we say polyglot, it really means that the whole Vert.x API is generated for all those languages using the constructs from this language for a natural integration. We have a simplified concurrency model based on an event loop. So you don't care about concurrency, you don't care about thread. It's going to use a minimum number of threads, and you will always, your code is going to be single-threaded. But as you are non-blocking, it's not a big deal. It's going to work. And it has a cluster event bus, and we are going to see that will enable the reactive system part. Vert.x is used today for microservices, web app, IoT, API gateway, high volume event processing, and many other applications. And if you're interested, go to http Vert.x.io and then scroll to who's using. You will see many companies are using Vert.x in production today for very different use cases. So why it's interesting in terms of reactive? It's because Vert.x was made to build reactive systems. We have reactive programming, and we implement reactive streams. So you have all three in one bundle. Everything comes from free. So let's have a look at how it looks like in a real application. So, and remember this application here. Let's re-implement it in Vert.x very quickly. So let's focus on this interaction first. Or my user get my product, and how do they insert my product? So let's imagine that my database has this API here, inserts that return a single, Eric's Java 2 single, when the insertion has been done. So I got a request, I do that on my database, okay, it's what I have here. And when it's done, once the insertion has been done, I just reply the 201, so created HTTP response. And if something bad happened because the database is not there or timeout, or so, I just fail the request. To list, so when my user wants to list the product, it will just say database.retrieve. This is return a stream of products. Okay, so with all the products, and then I subscribe. And something interesting here is that I don't want to overload my memory with the whole set of products. That would be very inefficient in terms of memory. So I'm using something that exists since HTTP 1.1 is chunked responses. As soon as I have a product, I'm going to write it down inside my HTTP response, so meaning that my memory will never blow up. Oh, by the way, I forgot to say, if you're interested by this code, it's there, so you use this GitHub repository. So yeah, as I said, as soon as I have a product that come back from my database, I'll just write it to my HTTP response, and it's my client side that will have to handle and display it correctly. Okay, but what about calling my pricer here? So let's have this first version where this is a web or a REST service or an HTTP endpoint, and I'm going to use the Vert.x web client for this. And when I retrieve my product, so this interaction here, for all the product, I'm going to call my pricer using my web client. So it's just a Vert.x HTTP client. So I get the price. I extract the price from it, and I produce a product out of that, and the rest of the code doesn't change. Pretty cool, because for each product, I'm going to use a web client, fine. All is non-blocking and asynchronous, and everything is fine. And as soon as I have the first response, or the sequence of response, I'm writing inside my HTTP response the product, and so on, using my chunk response. The issue here is that I depend on one process service, and this is not really what we had in mind with Reactive System, where we need to send messages to an address and not to a specific recipient. Vert.x comes with a clustered event bus, and instead of using the web client and so pointing to an URL, we can just say, hey, just send it to this address here, and whoever is listening to this address is going to reply to that one, to my message in an asynchronous way, and it's going to be the same type of interaction, except that no, we don't hard code the URL, we just use an address, and we can have one instance or X instances of my pricing service. It's fine, everything is fine, and the rest of the code stay unchanged. Let's continue in building this application here and say, yeah, we want to inform our users as soon as someone has added a product. Oh, but it needs a price too. So what can we do here is to say, okay, I'm inserting my product name. I'm retrieving the price of this one, okay, and now I have my product with the price. Writing the 201 HTTP response to say to my to the one writing it that okay, it's done, but I can do an additional things because this is not the last instruction. I can also say, oh, and I will announce this new product to everyone listening on this product's address. And the browser from all the user can also be part of the event bus using what we call event bus bridges, and so receive those messages, meaning that using a Suck.js channel receive all the new products without having to reload it. So how does it work? So Suck.js is a JavaScript library that will negotiate the channel between your browser and the application using WebSockets and then degrading to SSE and long polling and so on, depending on the capability of your browser. Okay, so, and also the last thing we were wanting to do is to call the audit system here. But what I can do is get the price and call the audit at the same time. I don't care to do that in a sequence. I can do that at the same time. And this is what is done by these 3 lines here. I get the price from product. That's a single. It doesn't do anything. Nobody's subscribed to it. That's my action to send the action to the audit system. Okay, again, it does nothing. Then I zip both stream, meaning that when both are done, I will continue. That's a stream, and then I subscribe on it, and everything will be done, will be executed. And both interactions happen in an asynchronous way in parallel, well, concurrently. So it's pretty cool because you don't have to think about it, about thread and so on. Everything is there and works perfectly well. So let's run this. So again, I'll show you the GitHub repository is exactly this code, and I'm going to run this. The pricer service is normally started, hopefully, yeah. We'll see that pretty quickly. So again, Vert.x is a toolkit. So I just wrote a main, deploy my vertical. So a Vert.x component, right-click, run. Don't need any plugin or anything. Let's go here. That's this one here, and yeah. There it is. So we got my products that were in my database, and let's try to add one. But before adding one, I will copy the same URL and open Safari here. And we should have the same set of products. Okay, now I just want to move you. Okay. And now I'm going to my terminal. I can't access my terminal from here. Or I just stop the screen sharing. That's not very convenient. Sorry about that. I will open a new terminal here. Where is my Safari? So that you can see everything at the same time. Okay. Okay. If I do, okay. If I want to add water, for example, boom, you see that what happened is that this one got the 201 response, as we said, okay, but also publish, the application publish on the event bus the new product and send it to both here and here at the same time because both browsers are connected using Sock.js to my event bus. It's very easy to do any kind of interactive application like that because you don't need to care about who is sending the event and so on. Here, I have one application, but if you're in a microservices system, any of your microservices can send an event on the event bus, and also a connected browser can get it. Let's go back to my slides here. All right, and let's conclude now because I'm a bit out of time. So what does reactive mean? Reactive is just a new way to build asynchronous system, but all the world is asynchronous. Everything you do is actually asynchronous. I'm speaking and you're receiving all my word asynchronously. When you are typing on your keyboard is asynchronous. Your operating system always dealing with interruption and so on is asynchronous too. So it's just another and very powerful way to build such kind of asynchronous systems. So reactive has many, many facets, and the main three ones are reactive systems on one side, which is, well, let's say distributed system done right to build responsive distributed system based on asynchronous message passing and elasticity and resilience. But implementing such kind of system can be hard. So we have reactive programming that will help you to build such kind of system at the code level. How do you develop it on a daily basis? How do you manage all this stuff? And reactive streams is actually very important when you have streams, because when you have something in your stream process that can't keep up, you need to slow down the whole chain, and not just a previous one, but the whole chain. And it's all our reactive streams can help you to build that. But again, if you are using a modern reactive programming library, no problem, because it's hidden for you. You don't have to do anything. You are just using Flow, Flowable, depending if you use Reactor or Alex Java 2, and you're done. That's all I have. If you are interested to go a bit deeper about Vert.x and about reactive and microservices, we published this book a couple of months ago. You can download it for free from this link here, or from this link here if you want to scan it. Well, enjoy, and if you have any question, I don't know how it works.
Clement, that's awesome. We do have a couple questions for you, though, and at least one that I think is super important because it comes up all the time, and that's related to back pressure. So for instance, in your last chart there, is back pressure specific to reactive streams, or can I implement back pressure and see it in other ways?
So that's actually a very interesting question. And if we can discuss today, like that, if I can present, it's because there is back pressure in the wire. TCP, which is the protocol implementing internet today, has actually back pressure. And so back pressure is not a new thing. And that is since the beginning of computer systems and network systems. Back pressure is a software way, reactive streams is a software approach to deal with non-blocking back pressure. But there is many other models. Typically in Vert.x, we have we have reactive streams, and we have another model based on pause and resume. So when you're full, you pause the stream, you continue processing, and when you're back on track, you just resume the stream. So you can implement back pressure differently, in a very different way.
Well, and I think that's probably a key point. You have to have back pressure support both at the consumer level and producer level. If the producer doesn't care about your back pressure, it will just ignore the message that says, "Please slow down, please stop."
And actually, today, there is one way, the most common way to deal with back pressure is to use Kafka. Kafka is a limited buffer or unbounded buffer where your writer will write inside and your consumer will consume the data at their own pace. So it's kind of a back pressure protocol, just using an unbounded buffer in the middle named Kafka.
Yeah, I love that point. And your demo, by the way, is totally awesome. I love how you can see where an event happening in one part of the system is immediately visible throughout the rest of the system. It feels like the nervous system of the body, human body kind of thing, right? That the event immediately ripples out.
Your body is reacting to stimuli. My system reacts to stimuli. They're the same thing. We just mimic the biological world.
Okay, well, that's all the time we have for today. We always like to keep these things short. I thank you guys all so much for showing up today. As you saw in the chat, if you're participating in the chat, we have people from all over the globe, and that's absolutely amazing. That's certainly why we do this, to make sure that this kind of content, this kind of valuable information coming from Clement today can get out to the world at large. And so thank you guys so much. Please feel free to download those books, check out the recording here on YouTube. If you have any questions or concerns, hit Clement or myself up on Twitter, or feel free to email us back on the same email you got from us when it alerted you to this session. So thank you for participating in DevNation Live today. Clement, thank you.
Yeah, thank you very much.